Okay. Section 6.2, Substitution, or the substitution method for integration. This allows us, this is a technique for integrating, probably one of the most useful techniques for integrating, that's going to let us take integrals of functions that we don't know how to take integrals of yet. And it's sort of like the analog of the chain rule for derivatives. Well, that'll make more sense after I do some problems. And what I want to do is just get straight into some problems. And kind of outline the process as I do these examples. Okay, so I want to integrate 4x times x squared plus 1 all to the 6th power. Now, we don't have a rule for this right now. We don't have a rule for this. My only hope of doing this integral right now would be to expand x squared plus 1 to the 6th out, and then multiply 4x in. After I do all of that, I would have this massive polynomial, and then I could find the integral of each term independently, but that would take forever. That's not the optimal way of doing this. Instead, what we're going to do is we're going to make a change of variables. That's kind of the key thing that we're doing here. By going to introduce a new letter, u, equal x squared plus 1. Now, why did I pick x squared plus 1? Whenever you're making your change of variables and you're letting this u equal some function of x, there is usually a right choice, but there's not any hard and fast rules that say what you have to let u be. Usually, though, if you see some function buried inside of another function, right, like this x squared plus 1 is buried inside of this power of 6, or if it was buried under a square root, or a natural log, or if it's in the exponent of some exponential function, you're going to want to let u equal that interior function. But that's not always the case. Sometimes, substitution is not making this change of variables, it's not a really concrete step. Usually, though, let u be the inner function. If you see some inner function, I'll put it in quotes here, inner function. If you see something that's inside of another function, let u be that. Okay, so why am I doing this? Well, the next thing I'm going to want to do, the point of this, so let me say this, the motivation, the point is to get rid of all x's. They need to be replaced with u. So right now I've replaced x squared plus 1 with a u, but I've also got this x, and I've got this dx, which is going to be the most important thing to get rid of, the dx, because this is what tells me what I'm integrating with respect to. So how do I get rid of dx? Let's not worry about the 4x right now. That's going to be an easy thing to get rid of. Let's worry about the dx. So how to get rid of dx? Well, consider u equals x squared plus 1. This is a function of x. It's u is a function of x here. U is a function of x. So I can take the derivative of u with respect to x. What does that look like? Derivative of derivative of u with respect to x looks like this, and that's going to be equal to, now over here you just take a derivative, 2x. So I literally took the derivative of this side, x squared plus 1. And the notation is du dx. I could write this as du dx. It's the same thing. Same thing. Just kind of wanted to make the point that I'm taking the derivative d dx. That means with respect to x. Okay, now you see a dx involved. That's good. That's good. Solve for that dx. Like literally just algebraically solve for dx. So I'll have du is over dx is equal to 2x. That's going to be the same as du is equal to 2x dx. Right, just multiplying by dx. So just kind of treating dx as a variable, multiplying by it on both sides. Now divide by 2x. Du over 2x. So this may feel like a kind of naive thing that you shouldn't be doing, like doing algebra with these, little, they're called differentials, but anyways, we don't need to know that. It seems kind of like bad form to be doing algebra with these things, but it's okay. It's okay to solve for dx this way. So now I can directly replace this dx with a function of u, or rather a du, and over 2x, this is a problem, but if I plug into the integral everything that I have now, let me get this integral of 4x times x squared plus 1 all to the 6th power dx is going to be equal to integral of 4x times u to the 6th, right? Because that's what I let u equal in the very beginning. And now dx is du over 2x. You see what's going to happen here. 4x, now this is all attached with multiplication, so I can reorder these and I can say this is 4x over 2x and then u to the 6th du. My change of variables, getting rid of all x's and making a change of variables to u, is almost complete here, because now this integral is just 2 u to the 6th du. There we go. This, we know how to integrate this. We know how to integrate this. We have the power rule for integration, and that's going to let us say that this is the same as, so remember that power rule for integration is if you have x to the n dx, that's the same as x to the n plus 1 over n plus 1. Oh, plus c. Dang it, I didn't leave room for my constant of integration. There we go. And this is the same thing, it's just a u instead of an x, and that's fine. This 2 is just going to get carried along, so it's going to be 2 times u to the 7th over 7. Remember how the power rule works for integration. You increase the power by 1 and then divide by that new exponent, and then plus your constant of integration. Now the last step is to reintroduce x. So I'm going to say this integral is 2 times u to the 7th, but u is x squared plus 1, right? By that, right? So in the end, you want to reintroduce that original variable that you were working with. There it is. So the integral of 4x times x squared plus 1 to the 6th dx is equal to 2 times x squared plus 1 to the 7th all over 7 plus c. What a strange process, right? But this is how it goes. This is how it goes. Okay. You let u equal some function of x, usually the inner function. Then you find the derivative of u with respect to x. Then you solve for that dx. Then you do a bunch of replacing in your integral. The extra x's should cancel out. You now have an integral solely in u with that du attached. See, that du is important. because if you want to integrate with respect to u, you need this to be du. And now there's no x's in sight. There's an extra 2 hanging around, but that's fine, it's just a 2, right? But the point is there's no x's. Now you integrate just like you normally would. It's just a new letter, right? That's it. So just a normal integral here. And then the last step is to put that original variable of x back in by replacing whatever you let u equal, in this case x squared plus 1, you reintroduce that right there. Alright, I want to do some more examples. Oh, and earlier I said that this is the sort of analog of the chain rule, right? So what I mean by that is if you take the derivative of this function, you would need the chain rule, right? So just to kind of prove that this is true real quick, let me take the derivative. This would be a good review for how the chain rule goes. Okay, derivative of this outer function with respect to the inner, that means I'm going to take this 7, drop it down, so I'll have 2 times 7, and then x squared plus 1 raised to the 6th all over 7. That's the derivative of the outer with respect to the inner. Then times the derivative of the inner, which the derivative of this will just be 2x. Now, cleaning all this up, these 7's cancel, 2 times 2 is 4, so I'm left with 4x times x squared plus 1, all raised to the 6th. Oh, by the way, the constant of integration goes away, right? Because it's just a constant, and I'm taking a derivative. So here's just a quick little proof that this, in fact, does equal this. There's my integrand. Alright, more examples. Tons of examples for this section. I'm following the book right now. Alright. Part A says integral of x squared times x cubed plus 1 all squared dx. Alright, your first step is to pick what to call u. Now, remember that tip I gave you was to let u be something that's on the inside, right? So let's let u be x cubed plus 1 here. Then find the derivative of u with respect to x. That's going to look like this. The left-hand side, this is the derivative of u with respect to x. Okay, then what is the derivative of this? That's 3x squared. Okay. Sorry. Okay. Okay. Now, solve for dx. du is going to equal 3x squared dx by multiplying by dx on both sides, getting it out of the denominator. Then du dividing by 3x squared. There we go. I've got dx solved for. Now I've got everything I need to go ahead and replace this integral. Let's see, x squared is still there, right? I did not make a direct substitution with x squared yet. I do, however, have this covered, right? This is squared. And then dx is du over 3x squared. Okay. And now you see how this integral, these x squareds are going to cancel, right? X squared and x squared. Can even reorder it as x squared over 3x squared times u squared du. And you see how these x squareds will cancel now, and I'm going to be left with 1/3 u squared du. And then now I can just integrate this like normal. I'm going to have 1/3 times u cubed over 3 and then plus my constant of integration. Okay, that's going to equal u cubed over 9 plus that constant of integration. Let me slow down here. Okay, so right here, what I did is I rewrote this integral, but I replaced x cubed plus 1 with u. That's what I defined it as. And I replaced dx with du over 3x squared. This is where the dx was. And I did not replace x squared because I did not make a direct substitution for that. But that's because I knew that from this right here, that x squared was going to end up going away. That's how these always work. That extra term floating around always gets canceled out from replacing your dx part. Okay, now once all that happens, I'm left with a 1/3, which is fine. That 1/3 is just a number, it's not an x, so it's okay that that is hanging around. Now I just integrate u squared du. That means I add 1 to the exponent, divide by that new exponent, and then that means that in the denominator here I've got 2 3's multiplied together, so that gave me the 9. Now finally, replace u, you got to reintroduce that x, that variable x, so you replace u back with whatever whatever you defined u as earlier. Okay. Okay. B. 3x times e to the x squared dx. Okay. Gotta pick u first. Gotta pick u. Remember, let u be that inner function. What is the inner function here? It's not the 3x, it's not the e to the x, it's not the e to the x squared. It's going to be x squared. That's the inner function. What's happening on the inside? Whoop, whoop. X squared. Let u equal x squared. Okay. Now that means that du dx, so the derivative of u with respect to x, is 2x. And then that means that dx, so pause the video, try to solve for dx here. You should get du over 2x. Okay. Now, replacing all this stuff in the integral, I'm going to get 3x times e to the u, right? E to the u. And then du over 2x. So I've replaced x squared with u because of this. I've replaced dx with du over 2x because of this. And now, see these x's, they'll cancel. I'll be left with integral of 3 over 2 times e to the u du. 3 over 2, and the x's cancel. But e to the u du, that's just e to the u, right? Integral of e to the u is just e to the u. There we go. So what I'm saying is this integral is very easy, right? Integral of e to the whatever the variable is. It's just e to the u plus the constant of integration. And the 3/2 just gets carried along. Last step, replace u with what it was originally defined as, so e to the x squared, and then plus c. Okay. What about part C? It says integral of 1 over (2x plus 5) dx. Okay, not as much going on here. What is the inner function? The inner function, it's going to be this 2x plus 5, the thing in the denominator. So u is 2x plus 5. So, here's a hint. let u be the function of x that is in the denominator, maybe. It could be in a denominator, under a root, under a radical, like a square root or something like that, in an exponent, like it was for part B, inside of parentheses and raised to a power, like it was for part A. Just anytime it's inside of another function, like this. It's in a denominator. Okay. Now here, what is the derivative of u with respect to x going to be? It's just going to be 2, right? 5 goes away, it's just 2. Solve for dx. Dx is going to be du over 2. Okay, now this integral then will be 1 over u. Now dx gets replaced with du over 2. Remember, everything here is attached by multiplication. Okay, there we go. So no other x's hanging around to cancel because we got everything taken care of. This is going to be 1, I can pull that 1/2 all the way out of the integral if I want to, and then 1 over u du. But remember, this is u to the negative 1, and that's that special integral that the power rule does not apply for. It's going to be ln of u, ln of absolute value of u, rather, plus c. And then replacing u with 2x plus 5. There we go. Okay, so remember the way I got this integral, the way I got 1 over u, the integral of 1 over u du to be ln of absolute value of u. So that's that special rule. It says for an integral of some variable raised to the negative 1, which is exactly what 1 over a variable is, right? That's going to be ln of absolute value of x plus a constant of integration. Okay. Let's do part D now, which is a sum of 1 over 2x plus 5 plus 4x squared plus 1 dx. Well, thing is we don't need the substitution rule for these two. Let's split up this integral into 1 over 2x plus 5 dx plus integral of 4x squared dx plus integral of 1 dx. Okay, this we already found, ln of absolute value of 2x plus 5. Oh, I forgot something. 1/2. There we go. 1/2 ln of 2x plus 5. This will give me, let's see, add 1 to the exponent, so it'll be x cubed, and then divide by that exponent. So 4 over 3 x cubed. See, there's the increasing the power by 1 and dividing by that exponent. Then plus integral of 1 is just going to be x, or whatever the variable of integration is. If it's dx here, then integral of 1 is just x. And then plus our constant of integration at the back of all of this. There we go. Okay. Okay. I'm going to keep following the book for now. I think I'm going to deviate at some point and just do a bunch of problems from the homework set to show you more examples. Evaluate integral of x plus 3 times square root of x squared plus 6 dx. Okay, so we need to decide what u is going to be. We have something wrapped in parentheses, and we also have something buried under a radical. Now, think about what you're going to do to the letter u, to the variable u. You're going to take its derivative, right? And the point is that that derivative should cancel out one of these, right? So if I let u equal x plus 3, then the derivative will be 1, and that's not going to cancel anything. But if I let u equal x squared plus 6, I might be in better shape because the derivative of x squared is 2x. That gives me an x to work with to try to cancel that out. This isn't going to work though, because I wrote it down wrong. That should be an x. I was about to say this isn't gonna work. There we go. Now it'll work. Okay. So du will be, du dx, derivative of u with respect to x will be 2x plus 6, just taking a derivative there. Usually this step should be very quick, just a little derivative. Then solve for dx. You're going to get du over 2x plus 6. Just multiply dx times this whole thing, and then divide this whole thing over du over 2x plus 6. By the way, let's note that that is the same as du over 2 times x plus 3. And surely you see why I want to make that distinction and point out that if I factor a 2 out of this, I have x plus 3. Because now these match. Usually these problems are set up to do that. Okay, now I'm ready to replace in my integral. I've got x plus 3 times square root of u, and then dx gets replaced by du over 2 times x plus 3. X plus 3's are going to cancel. Now it's tricky canceling things that have sums in them, or differences, right? Everything has to be exactly the same. But they are. Since I factored that 2 out, everything is exactly the same here and here, so I can cancel these terms out. And I'm left with integral of square root of u over 2, because that 2 is still down there, and then du. In fact, I can even, this over 2, I can pull that out as a 1/2, and just store it out there so I don't have to think about it while I'm taking my integral of the square root of u. By the way, what is the integral of square root of u? Well, that's the same as integral of u to the 1/2 du. Now that I have it written with its power noted, with its exponent noted, I can use the power rule, which says I should add 1 to this. So let me write my 1/2. Okay. Add 1 to it. So 1/2 plus 1 is 3/2, and then divide by 3/2, and then plus my constant of integration. What the heck is going on here? Well, that's the same as when you divide by 3/2, that's the same as multiplying by 2/3. There we go. That looks a lot better. So whenever you're dealing with square roots and cube roots and radicals, you're going to be dealing with fractional exponents. So a really good rule of thumb to remember is that when you're doing your integration, you're going to have to add, right? Add 1 to the fraction. But then you're going to have to divide by a fraction. So it's really helpful to remember, especially for all these radical problems, that when you're dividing by this fraction, that's the same as multiplying by its reciprocal, by its multiplicative inverse. Okay, now clean this up, and I'm going to replace u with x squared plus 6x. So I'll have 1/3 times x squared plus 6x raised to the 3/2 plus c. By the way, the 1/3 came from these 2's canceling, right? These 2's. Just leaving me with 1 over 3. Okay. Let's keep going. Okay. Okay, example 4 is another substitution problem, but it's kind of a specific situation, which is good. We're going to look at it, but before I do that, let me go look at some problems from the text, just to do some more straightforward ones. I'm going to do some even ones. So let's do integral of 2x plus 5 raised to the negative 2 dx. Oh, and they tell you what to use for u here. Okay, whatever. Okay, so we're going to let u equal 2x plus 5, because what else can you really, oops, what is that? What else can you really do here besides letting u equal 2x plus 5? Then the derivative of u with respect to x is going to be equal to 2, just derivative of this. Then dx will be equal to du over 2. Now I'm ready to replace all the stuff in my integral. I'm going to have u to the negative 2, right? U to the negative 2. dx is replaced by du over 2. I can pull this over 2 all the way out as a 1/2, and then I have integral of u to the negative 2 du. Now I can use my power rule on this, add 1 to the exponent, and then divide by that exponent. Okay, so there's the power rule. So it's okay to use the power rule on negative exponents. The only one you have to watch out for is if you're integrating something to the negative 1. That's when you use the ln rule. So here this is going to be equal to negative 1 over, or how about negative u to the negative 1 all over 2 plus c. Right, this negative coming from the negative down here. The over 2 coming from the 1/2 here. And u to the negative 1 is right there, u to the negative 1, and of course plus c. And then replacing u with 2x plus 5, I'm getting negative, parentheses, 2x plus 5, raised to the negative 1 all over 2 plus c. There we go. Let's see. Okay, they're talking about some sort of shortcut in the next few problems. You don't need a shortcut. Okay. Let's try number 6, another straightforward one. E to the x over 2 dx. Okay, so what is the inner function here? It's this exponent. So let's let u equal x over 2. Then du dx, the derivative of u with respect to x, is just 1/2. Right? X over 2, the x just goes away, right? It's a linear function, so we just get 1/2. That means that dx is going to be equal to 2 du. So I would make sure you can solve this by yourself, getting from here to here. So multiplying by dx on both sides, and then multiplying by 2 on both sides. That's how I got here. Now I'm ready to do my replacing, so e to the u, because x over 2 is replaced by u. dx is replaced by 2 du. I can pull that 2 all the way out, e to the u du, but e to the u du, or the integral of e to the u du is just e to the u. So 2 gets attached. There we go. And then replace u with the function of x. There we go. Let's see. How about number 10? Yeah, they're in the other problems that I'm skipping, they're talking about using a shortcut for things that have linear inner functions, and that's fine. I'm probably not gonna talk about that too much, because to me it's just throwing a whole nother type of problem for you to be on the lookout for. Just stick with the substitution rule in general. It works for all the problems that they're going to throw at you in this section, it's going to work for all of them. So no need to introduce a new rule, in my opinion, because it doesn't make things that much easier anyways. Okay, so what is the inner function here? Well, we have options. Could be x minus 1 cubed or x minus 1 squared. But think about when you take the derivative, because eventually we're going to take the derivative of u with respect to x, that derivative is going to drop the power by 1, and then whatever's over here, I'm going to want to cancel one of these things, right? So how is this going to work? I've got to let it be x minus 1 cubed. X minus 1 cubed. That way, over here, when I take the derivative, now I've got x minus 1 squared, and you know that matches here. That's good. That's good. That means that somehow this is going to end up canceling with this. By the way, what is dx going to be equal to here? This implies this. You'll multiply by dx and then divide by this whole thing. So du over 3 times x minus 1 all squared. Okay. Now, rewriting the integral, I've got x minus 1 all squared times e to the u, and then dx is du over 3 times x minus 1 all squared. So take a second, make sure you see how I replaced the exponent of e with u, and how dx got replaced by this. Okay, now you're going to see how, now you will see how x minus 1 squared cancels with this x minus 1 squared. They're exactly the same. So I'm getting, by the way, I can pull this 3 all the way out. It's in the denominator, so it's a 1/3. And then just e to the u du. That's all that's left, right? This and this go away. E to the u du. 3 is all the way on the outside. This is going to be just e to the u plus our constant of integration. And then replace that u with x minus 1 all cubed. And there we go. There we go. Okay. Let's do example 4 now. Let's back up to example 4, because it is an interesting little technique they use there. This is not the shortcut. This is just a kind of a new situation that can arise. Let's evaluate integral of 2x over x minus 5 squared dx. Okay. I'm going to let the u be, well, we could let it, I think that's their point. Okay, let's let u equal, let's let u equal x minus 5. See, the thing is, you could let u equal x minus 5 all squared here, but they're making a point about what can happen if you choose u to be this. So I'll play along and let u equal x minus 5. Then derivative of u with respect to x is just 1. And that's just going to imply that dx is equal to du, because I'll multiply by dx on both sides, and that's what I get. Okay, then making my substitutions, I'm going to have 2x over u to the second power, and then dx just turns into du. But now I'm in a situation where okay, where were we?
Can we get lunch?
Yeah. Okay, so this is a problem because the 2x, or well, specifically the x, is not canceled out by anything. Usually it would be canceled out by something hanging around over here, but there's no such luck. So the suggestion this example makes is, well, u is equal to x plus 5, right? So what do we do here? Well, u is equal to x plus 5. No, x minus 5. So why not let x equal u plus 5, right? Add the 5 over. Then we can say 2 times not x, but u plus 5 over u squared du. And then that's the same as distributing the 2u plus 10 over u squared du. And then that's the same as integral of 2u over u squared plus 10 over u squared du. Okay, just splitting the fraction. And then that, oh, yes, so this is parentheses around these. Now I can split the integral into, now these u's will cancel, so I'll just have 2 over u du plus 10 over, integral of 10 over u squared du. Okay. So the idea was to get rid of the x by kind of cheating a little bit and using this, where we defined u in terms of x, kind of reverse engineering that and getting x in terms of u, and then directly replacing this x. That's not always going to work, but it's a nice little technique. Now we need to finish this off. Integral of 2 over u du will be 2 times ln of absolute value of u. Okay, then plus 10 times, this will be, that's u to the negative 2, so negative 1 times u to the negative 1. Well, this is actually technically divided by negative 1. Whoops. Doesn't really matter though, does it? And then plus c. Okay, so I can clean this up to be 2 times ln. Now let me replace u with x minus 5, so absolute value of x minus 5 plus negative 10 times x minus 5 to the negative 1 plus c. Okay. Let me clean it up a little bit more. 2 times ln of absolute value x minus 5 minus 10 over x minus 5. Because x minus 5 to the negative 1 is over x minus 5, and then plus c. Alternatively, you could have just let u equal x minus 5 squared, and then derivative of u with respect to x will be, oh wait, this isn't going to work either. Let's see, 2 times x minus 5 okay, and then that would mean that dx is equal to dx is, so you would multiply du over 2 times x minus 5, which is the same as du over 2x minus 10. Yeah, this actually isn't, no, this wouldn't do it, because the 2x and the 2x won't be able to cancel because of that minus 10. So, thought we could get away with doing it this way, but nope, have to do it the other way. Okay. Alright, I'm going to do some more even problems now from the text. So integral of negative x minus 1 to the 7th dx. Let's let, I'm going to go kind of quick through these. Let's let x, or u equal negative x minus 1. Then du over dx will be just negative 1. That implies that dx is equal to negative du. Okay, that means that when I do all of my replacing, I'm going to have u to the 7th, and then negative du, but why don't I just put the negative all the way out there? Because it's just a negative 1, so I'll just go all the way out with it. And then this is going to be negative u to the 8th over 8, and then plus my constant of integration. That's using the power rule for integration. Then replacing u. sighing. 16 is integral of 8.1 times radical 3x, or square root of 3x minus 4 dx. Oh, my bad. It's negative 3x plus 4. Negative 3x plus 4 dx. Yeah. Okay. Let's see, we can let u equal negative 3x plus 4, then du, derivative of u with respect to x, will be negative 3. That implies that dx is equal to du over negative 3. Okay. And then this turns into integral of 8.1 times square root of u. Dx is du over negative 3. Let's get these constant numbers all the way out. So 8.1 over negative 3, then integral of square root of u du. That's going to be negative 8.1 over 3. Integral of u du, that's going to be this is u to the 1/2, so add 1 to 1/2 in the power to get 3/2, then divide by 3/2, which is the same as multiplying by 2/3. And then we're getting this crazy answer, which is, what's 8.1 times 2? 16.2, so negative 16.2 over 9. 3 times 3 is 9. And then u to the 3/2, but u is negative 3x plus 4. So negative 3x plus 4 to the 3/2, and then plus c. That's a different one. Okay. Let's see, what else? What's another good one? About 28. X times e to the 2x squared minus 1 dx. Okay, let's let u equal that exponent, 2x squared minus 1. Then du with respect to x, derivative of u with respect to x, is going to be 4x. That implies that dx will be equal to du over 4x. Now replacing everything in the integral, I'm getting x times e to the u, and then dx is du over 4x. X's cancel. I'll be left with a 4 in the denominator. Let me go ahead and pull that 4 out as a 1/4 because it's in the denominator. And then I just have e to the u du, but that's the nicest integral because that's just e to the u plus my constant of integration. And then just replace u with 2x squared minus 1, and then plus c. Okay. Any other good ones to look at? That's pretty good. How about 38? I'll do one more. 38. X over square root of x plus 1. Yeah, this is going to be kind of like example 4. Let's let u equal x plus 1. So derivative of u with respect to x is just 1. The number attached to this x. So then that implies that dx is equal to du. Direct substitution there. So we're getting integral of x over square root of u du. That x, that's a problem, right? X is still there. But can say that x is equal to u minus 1 from this equation. So this is just like example 4, where you have to do that weird thing where you let x be some function of u so that you can replace any extra x's floating around. So I'm getting integral of u minus 1 over square root of u du. Now it's all in terms of u. So now I can say this is the same as integral of u over square root of u du minus 1 over square root of u du. So I split the fraction and then split the integral. Did that all in one step here. So u over square root of u, then minus 1 over square root of u du, both ending with du. Now note that u over square root of u is just square root of u. So u over square root of u is just square root of u. That's because this is 1/2, right? So this is the same as u to the first minus 1/2, which is equal to u to the 1/2, which is equal to square root of u. So u over square root of u is equal to square root of u. It's one of those weird things about square roots. Okay. Now integrating each of these, I'm going to get, for this one, I'll get 2/3 u to the 3/2. And for this one, I'll get, now this is a negative 1/2 here. So I'm going to add 1 to that, giving me u to the 1/2, and then divide by 1/2, which is the same as multiplying by 2. So this is u to the negative 1/2. This u to the negative 1/2. And the power rule for integration says to add 1 to this, which would make it a positive 1/2, and then divide by that new power. And dividing by 1/2 is the same as multiplying by 2. So there we go. Here's all set up, and now replace u with x plus 1. There we go. Alright, so in the next video for this section, I'll do some applications of the substitution method.